Hi, my name is Jim Talius, and I am talking about the clutch mechanism inside of the mechanical pencil that we've selected. It's actually a double clutch, which just means that there are two different points.
Hello, my name is Max, and today I'm going to be presenting our free body diagram for the lead sleeve, which is the metal tube at the end of the pencil from which lead gets advanced out of. The reasons.
Hey everyone, my name is Ronnie, and I will be presenting the metal clip component of the Graph Gear 1000. As you can see here in the red circle, this clip I will be talking about. Clip uses include keeping track of the pencil, because with the clip you're able to clip it onto your shirt pocket, your jean pocket. The clip is also used to prevent the pencil from falling on the ground, because if the clip wasn't here, it would just roll away, drop on the ground, and then cause damage to either the tip or anywhere else that could cause the pencil from not working. There is two failure modes to this component. The first one would be the clip breaking. It has a risk priority number of 24. Causes include wear and tear or the clip getting caught onto things. The effects would be unsafe sharp edges, like this guy right here. Probably cut you. It'd be less visually appealing, and then you wouldn't be able to clip it onto anything anymore. Failure mode 2 would be bending out of shape. This one has a risk priority of 60. The cause would be excessively bending the clip with your thumb or some other way. The effect would be not being able to clip it onto anything, just like failure mode number 1. Here we have the metal clip free body diagram. The assumptions we made for this is that the human force will come from the user's thumb. The human force will be placed at the farthest point on the shorter end, so over here. And the clip is free to move. Here, this line represents the clip. So this horizontal line would be the clip. The clip is 4.2 centimeters long, and when there's a human force exerted on the clip on the shorter end, there is a force coming out, which would be this guy. And there's a moment about this point or this joint, MC. We also have a few more dimensions. So from the joint to the leftmost point would be 3.1 centimeters. And over here on this end, it would be 1.1 centimeters from the joint to the rightmost point. And this joint represents where the clip is connected to the rest of the mechanical pencil. Furthermore, we have the free body diagram calculations. After doing some research, we found out that a typical thumb, or I would say just the thumb, can create 10 newtons of force. So here we did the calculations for the vertical forces. So the vertical forces in the y direction equal 0, which would be F out minus FH, because F out's going up, FH is going down. And then we solve it for F out, which would be 10 newtons. And then the sum of the moments about C, where the joint would be F out times 3.1 centimeters plus FH times 1.1 centimeters. We further go down here and we get the moment about C is 42 Newton centimeters or 0.42 Newton meters. And that is it for this part of the presentation. I will pass it on to my peer now. Thank you for listening. Bye.
I'm going to give you a breakdown on the Graph Gear 1000's collar. The collar is the part that's highlighted in yellow here. It is a part that is really responsible for the pencil actually working as intended. You can kind of see it's in really the core center of the pencil, um, with number 4 being where the lead actually comes out, and 5 being our part which goes around it. What does it do? This collar is essential to the pencil actually performing its function, writing. It holds the lead in place so it doesn't get pushed back inside or slip at all when it's being held properly. But then it also allows the functionality to also be able to push more lead out when you need, so you can continue writing. It also keeps the lead centered, so there's no wobble back and forth, so you can really guide it, and ensure that it actually does come out of the tip of your writing implement reliably. Common forms of failure for this, really the biggest one is deformation, or and just wear and tear on it. It's kind of either between getting compressed in some way, like what's seen here, or also friction. That was just really hard to just kind of represent in this sense, but it's primary for this part working to have a firm hold on the component that pushes out the lead. And so if it loses that strong hold, then you'll have slippage and you'll have unreliability. And it's very clear to see if there if you had deformation, some form of ellipse, like here, you wouldn't be getting that really even distributed hold on the lead clampers, I guess. And you wouldn't have an even hold on those, which means that you wouldn't have a reliable or consistent writing experience. Here's my free body diagram that I kind of did. Assuming it's in 2 positions, one with the lead holder or with the clamps open and one with them closed. The way that those actually open and close with that collar, or sorry, with the collar staying fixed and those being pushed forward. And so when they get pushed forward, the forces decrease, um, and they open up, allowing the lead to slide out. But when it's closed, there's a lot more force enacting on the collar, which is why the forces are greater, because it's making sure that the lead is held in place. Um, yeah, and then assumptions. It's in either extreme state. There wasn't um, any calculations or anything done in any of the various in between states. We're assuming axial forces only, no shear torque forces, just because by the time it gets inside the pencil, it doesn't matter what angle you're writing on. There's really only going to be linear forces going through that. And then also that the axial forces will be roughly 0.01 when the lead is being extended, just because there's minor forces, and 0.05 when the lead is being held in place, just due to the nature of that spring and everything. But yeah, that's the color presentation.